Somewhere on a server right now, a piece of code you did not write is about to run directly inside the operating system's kernel. The most trusted, most dangerous part of the whole computer. One wrong move there, and it is not an app that crashes, it is the entire machine. So here is the question this video is actually about. How does Linux let strangers' code run in that space thousands of times a second on servers at Cloudflare and inside every pod in a Kubernetes cluster without it ever taking the whole system down? The answer is that before any of that code gets anywhere near the kernel, it has to survive something that looks a lot like a courtroom cross-examination. Picture the code as a defendant on trial, and the judge is a piece of the Linux kernel itself, called the verifier. The whole system is called eBPF, extended Berkeley Packet Filter, and it did not start as a courtroom at all. Its ancestor, classic BPF, was described in a 1993 paper by Stephen McCann and Van Jacobson, and for 2 decades it did one narrow job: deciding which network packets a tool like TCP-dump was allowed to look at. Then in 2014, Alexei Starovoidov and Daniel Borkman proposed something much bigger to the kernel's networking maintainer. Keep the same trusted sandbox, but let it run general-purpose logic, not just packet filters. That proposal became eBPF, and the sandbox became a full legal system. Before the verifier lets a single instruction run, it asks the defendant the oldest question in computer science. Are you guaranteed to finish? According to the kernel's own verifier documentation, the first pass is a depth-first search through every possible path the program could take. And it throws the case out immediately if it finds unreachable code, an unbounded loop, or a jump outside the program's own boundaries. This is exactly the kind of check that used to be optional for kernel code. Here it is mandatory, and there is no appeal. There is also a budget on how big a case the court will even hear. For years, the verifier would only work through a few thousand instructions before it gave up and rejected the program outright. In 2019, with kernel version 5.2, that budget was raised to roughly 1 million instructions for trusted, privileged programs. Same courtroom, just a lot more patience. Surviving round 1 only proves the program stops. Round 2 is about what it is allowed to touch while it runs. The verifier's second pass actually simulates the program, instruction by instruction, tracking exactly what is in every register and every slot of memory at each step. If at any point the simulation shows the code might read from a pointer that could be invalid or null, or right outside a buffer it was given, the whole program is rejected before it ever executes for real. Nothing gets the benefit of the doubt. The court does not wait for the crime to happen. It rules it out in advance. And even a program that behaves perfectly on its own cannot just say anything it wants to the kernel. It can only call a fixed, pre-approved list of kernel helper functions. Which functions are on that list depends on what kind of program it is. A program attached to a network card hook gets a different witness list, different memory rules, and a different verdict path than one attached to a security policy check, or one just watching function calls for a monitoring dashboard. One judge, many kinds of trials, all held to the same standard of proof. Nothing off that list is allowed to testify. Once the code passes every round, the case is closed, and the verdict is enforcement, not permission. The kernel just in time compiles the verified bytecode into native machine instructions for the actual CPU, then attaches it to a hook. A specific point in the kernel where events happen. A network card receiving a packet, a function being entered, a container's network namespace. From that moment on, it runs at close to native speed, inside the kernel, without ever needing a kernel module, and without a recompile or a reboot. This is not a courtroom nobody uses. Look at the case files. Cilium, a Kubernetes networking project, uses eBPF to replace the old way Kubernetes routed traffic to your pods, which relied on iptables rules that had to be rewritten as a giant chain every time a service changed. eBPF instead keeps that routing table as a hash map inside the kernel, so adding one more destination is a single direct update instead of rewriting the whole chain. Here is the aha moment. That is the difference between updating one line in a phone book versus reprinting the entire phone book every time one person changes their number. Second case file. Cloudflare uses eBPF through a hook called XDP, which runs at the earliest possible point a packet touches the network card to drop attack traffic before it ever reaches the rest of the operating system's networking stack. Cloudflare's own engineering blog documented dropping 10 million packets per second on a single processor core using this technique. That is not code running fast. That is code running in the one place fast enough to matter. The verifier's job was never to prove your code is correct. Its only job is to prove it is safe. That it cannot crash the kernel, leak memory it should not see, or run forever. That is a narrower promise than it sounds, and it means the verifier sometimes rejects code that would actually have been fine because it could not prove it in time. Engineers work around that by writing simpler, more provably bounded logic, which is really its own kind of discipline. It is also worth knowing the judge itself gets checked. In 2024, the security firm NCC Group carried out an independent audit of the verifier's own code, commissioned by the Linux Foundation, precisely because so much of the kernel's safety now rests on this one piece of software getting its job right. Even the courtroom answers to an inspector. So next time some DevOps tool claims it can observe your entire system with almost no overhead, you will know what is actually happening under the hood. Somewhere, a piece of code just survived a cross-examination, and the kernel let it take the stand. Follow compile for what's under the hood.